So the glucose molecule has been through glycolysis. The 6-carbon glucose during glycolysis was converted to two 3-carbon pyruvate molecules. The pyruvate molecules were brought into the mitochondrial matrix where they went through a oxidative decarboxylation that yielded two acetyl-CoA molecules, and these two acetyl-CoA molecules are now going to the Krebs cycle. So whatever you see as product of this process, keep in mind that per glucose, you made two acetyl-CoA molecules. So everything that's produced is multiplied by 2 if you're doing the count by glucose. Now, again, to reiterate, this process takes place in the mitochondrial matrix. It produces ATP by substrate level phosphorylation. Just to review, substrate level phosphorylation means that an enzyme is taking a phosphate off a molecule and putting it on ADP to make an ATP. Now, in the Krebs cycle, this happens indirectly, but it happens this way nonetheless. Now, this process produces many NADHs and FADH2s, which are electron carriers, and here they are in the reduced form. Let's begin. Now, the PDC, or the pyruvate decarboxylation complex, yielded acetyl-CoA. Acetyl-CoA, each acetyl unit has 2 carbons. The 2-carbon acetyl unit binds to a molecule called oxaloacetate. Oxaloacetate, which has 4 carbons. Now, oxaloacetate bound to acetyl will form a 6-carbon molecule called citrate. Citrate goes through the first reaction, first and second, to produce a carbon dioxide. So here we have a decarboxylation. So 2 carbon unit molecules brought in, we lost our first carbon right here. Now, second step, we have an electron carrier, NAD+, coming to take 2 electrons and to become reduced. So here our electron carrier is reduced. Here is oxidized and here is reduced. So you can tell that this reaction is a redox reaction. This was a reduction, so this is an oxidation. Now, we've lost a carbon, so now we have a 5-carbon unit. It goes through a third reaction that produces carbon dioxide, so we have another decarboxylation. We have lost our 2 carbon units that came in. 2 came into the cycle, 2 came out to later regenerate our 4-carbon oxaloacetate. So we lost a carbon here, we lost a carbon here. This is a decarboxylation, and here we are again. Another redox reaction. NAD+ is being reduced to NADH, and a molecule here that shall remain nameless, thankfully, for grade 12 level, will be oxidized. In the next step, an ATP is produced. Technically, it is not an ATP. It is a GDP that gets phosphorylated to make a GTP, sorry. And then that GTP loses its phosphate, it yields it to an ADP to make an ATP. Alright, now we have a 4-carbon unit. We go to the next step, an FAD, another electron carrier in the oxidized form, gets reduced. So this is a reduction reaction, which means this is an oxidation. So now we have an FADH2 being produced, and in the next step, we have an NAD+ being produced. Now being reduced, sorry. Let's do the count. Per glucose molecule, we have 2 acetyl-CoAs. And each one will go into the Krebs cycle. Now, each Krebs cycle produces 3 NADHs, 1 FADH2, and 1 ATP, produced by substrate level phosphorylation. Now, in the next video, finally, we are going to discuss what is the use of these electron carriers. What is the use of producing all these NADHs, all these FADH2s? Why are we making these? I like to liken them to checks. They're not useful right away, but later on you will go to the bank and you're going to cash them out. So ATPs are cash, FADH2 and NADH are our checks. Cash is directly useful, but checks have to go to the bank. The bank is the electron transport chain. Stay tuned for my next video.